In all this compound, the metal cation are octahedrali surrounded by ligand and EG orbital unsymmetrically filled. Therefore, there are two longer bonds on z-axis and four shorter bonds on x and y-axis. The Jahan-Taylor theorem does not predict which type of distortion will take place. A nickel 2 complex surrounded by 4 strong and 2 weak ligands undergoes tetragonal distortion, but not due to Jahan-Taylor distortion because Eg orbital dx2, y2 and dz square are not electronically degenerate. The varying electron repulsion between the non-equivalent ligands and the d electron of the metal cation split the Eg orbital to a greater extent and T2G to a small extent as shown in figure 4.12. In this case, the magnitude of delta exit pairing energy P if all the 6 ligands are weak, then nickel 2 form a regular octahedral complex. On the other hand, if all the ligands are strong, then nickel 2 form a square planar complex. Electronic arrangement in A weak octahedral fields and B tetragonal nickel 2 with strong and weak ligand. Doctor, the complex in which T2G orbital electronically degenerate, that is asymmetrically filled, also undergo Jahan-Taylor distortion, but the distortion are very weak to be observed because the T2G orbital do not point directly at the ligand and relatively less affected by the ligand. The D1, D2 low spin, D4 and D5 high spin D6, D7 octahedral complex undergoes slight or weak Jahan-Taylor distortion. The octahedral complex of D1 configuration show Z in distortion. In this case, Z out distortion does not remove the degeneracy since even after distortion there are two dyz and dzx orbital which are available for the electron to occupy. The octahedral complex of D2 configuration shows head out distortion. The two orbital dxz and dyz having one electron each remove the degeneracy since both these two orbitals have z components and repel the ligands more strongly on z axis than the ligand on x and y axis. For the same reason, relative weak distortion are expected in tetrahedral complex with D3, D4, D8 and D9 configuration. In the D3 and D8 tetrahedral complex, one of the T2 orbitals has one electron more than the others, which cause an elongation in tetrahedron. On the other hand, the D4 and D9 tetrahedral complex, one of the three T2 orbitals has one electron less than the other. This situation causes a flattening of tetrahedral complex, static and dynamic Jahan-Taylor distortion. Some complexes show tetragonal distortion under all conditions, that is in solid as well as in solution, either at lower or relative higher temperature. This distortion is called the static Jahan-Taylor distortion. In this complex, the splitting of T2G and or EG orbital is quite high, so that the thermal energy available will not be sufficient to affect the population of orbitals in a distorted geometry. This type of Jahan-Taylor distortion occurs when EG orbitals are electronically degenerate, since distortion is strong and permanent. There are some exceptions to Jahan-Taylor distortion, in which certain physical properties correspond to symmetric structure when distortion are expected. In this complex, no distortion can be detected at room temperature because direction of distortion, say an elongation of one axis of an octahedron, randomly move among the available symmetry axes of the complex more rapidly than the physical measurement. In this complex, the thermal energy available at room temperature causes to equalize the population of the complex ion in the tetragonal elongator and tetragonal compressed geometry. This is called dynamic Jahan-Taylor distortion. Thus, the physical measurement detect an average structure with no or weak distortion. The distortion can be detected at freezing temperature because cooling of the compound will show oscillation enough resulting in a single distorted structure. Dynamic Jahan-Taylor distortion occur in complex in which splitting of T2G and or EG orbital is small. For example, The complex titanium H2O6 3 plus and FeH2O6 2 plus show dynamic joint Taylor distortion and appear octahedral in this complex. Both the type of geometry, that is tetragonal elongation and tetragonal compression, exists in equilibrium. In this complex, the distortion is small since the degeneracy occurs in T2G orbitals. Square planar complex. Square planar complex in an octahedral complex of nickel 2 with weak ligand. The electronic configuration of nickel 2 is T2G6 Eg2, that is T2G and Eg orbital are symmetrically filled. The electron density in dz2 orbitals along z-axis is greater than that of dx2y2 orbital along the x and y axis because dz square orbital is a linear combination of dz square square and dz square y square orbital. Electron density in dz square orbital will repel the ligands on z-axis more strongly, whereas the electron density in dx square y square orbital will repel the ligand on x and y axis to a lesser extent. Therefore, the distance between the metal cation and ligand on z-axis is larger than that on x and y axis. Thus, energy of dz square orbital become lower relative to the dx square y square, that is, there is a splitting to Eg orbital. But in case of weak field complex like nickel H2O6 2 plus and nickel NH3 6 2 plus, the splitting is small because charge on metal cation is not high and the ligand are also not too strong. Therefore, this complex are considered to be regular octahedral and energy of dz square and dx square y square will be same. That is, Eg orbital are degenerate, but if the ligand are sufficiently strong, difference in energy between these the difference in energy between these two orbitals becomes larger. An unpaired electron in a dz square y square orbital can drop down and pair with the electron already in the dz square orbital. Now the dx square y square orbital become empty. Therefore, a strong ligand can approach the metal cation along x and y axis without any difficulty as the dx square y square orbital is empty. The ligand approaching the metal cation along z-axis experience a very strong repulsion from the field dz square orbital. Thus, only 4 ligands can form bond with the metal cation. The amount of tetragonal elongations and the splitting of the d orbital depend upon the nature of metal cation and the ligand. The metal cation with the 8 configurations form square planar complex with strong ligands such as Cn minus nickel 2 from square planar complex. Nickel Cn4 2 minus with strong Cn minus ligand. Since first crystal field splitting for 4D 5D series transition metal and for highly charged metal is very large. 2. Ligands repulsion are minimized due to larger size of the metal. Therefore, all the complex of palladium 2, platinum 2, rhodium 3 are square planar respectively of the nature of the ligand, that is, whether the ligands are weak or strong. The crystal field splitting in square planar complex is shown in figure 4.10. In square planar complex of cobalt 2, nickel 2 and copper 2, the energy of dz2 orbital is nearly same as dyz and dzx orbital, whereas in square planar complex of palladium 2, platinum 2 and rhodium 3, energy of dz2 orbital is lower than that of dyz and dzx orbital. Delta Sp is equal to delta 1 plus delta 2 plus delta 3. The spectroscopic results have shown that delta Sp is equal to 1.3 delta 0, that is delta Sp greater than delta 0. Consequence of Jahan-Taylor distortion. First, stability of copper 2 plus complex. For a given ligand, the relative stability of complex with dispositive with dipositive metal ions of first transition series. Follow the order barium 2 plus smaller than strontium 2 plus smaller than calcium 2 plus smaller than magnesium 2 plus smaller than manganese 2 plus smaller than iron 2 plus smaller than cobalt 2 plus smaller than nickel 2 plus smaller than copper 2 plus greater than Zn2 plus. This series is called the Irving-Williams series. The extra stability of copper 2 complex is due to Jahn-Teller distortion. During the distortion, two electrons are lowered in energy, while only one is raised an equal amount of energy. The complex copper En32 plus is unstable because Jahn-Teller distortion causes strains into ethylene diamine molecules attached along the z-axis. Figure 4.13 is showing that larger bond causes strains in the complex along z-axis. In similar manner, trans copper En2H2O2 plus is more stable than the cis. The copper En2H2O2 because Jahn-Teller distortion causes strains in ethylene diamine molecule along z-axis in cis copper En2H2O2 plus. No strain, stable, strain less stables. Third, in the crystalline potassium copper trifluoride, the two copper fluoride distance on z-axis are 1.96 Armstrong and the remaining four copper fluoride distance in xy plane are at 2.07 Armstrong. It is due to Jahn-Teller compression. Fourth, complex of Orium-2 ions are unstable and undergo disproportionate of Orium-1 and Orium-3, whereas the complex of copper-2 and silver-2 are comparatively more stable. It can be expected to be the same stability of Orium-2, copper-2 and silver-2 complex, since all they have D9 configurations and undergo Jahn-Teller distortion since delta value increase on moving down the group. Therefore, delta value for Orium-2 complex is maximum among the three. The high value of delta causes a high destabilization of the last electron in the d square y square orbital. Therefore, Orion-2 complexes all have D9 configuration and undergo Jahn-Teller distortion since delta value increase on moving down the groups. Therefore, delta value for Orion-2 complex is maximum among the three. The high value of delta causes a high state destabilization of the last electron in the dx square y square orbital. Therefore, Orion-2 become extremely reactive and undergo either oxidation of Orion-3, a D8 system, or reduction to Orion-1, a D10 system. The Orion-3 form a square planar complex, whereas Orion-1 form a linear complex. The splitting of absorption bands in electronic spectra of complex due to Jahn-Teller distortions. Application of CFSC. First, enthalpy of hydration of transition metal ion. In an aqueous solution, the metal cation are surrounded by a polar water molecule. This process is called as hydration. There are 6 water molecules in the primary hydration sphere around the metal cation to form an octahedral aqua complex. Hydration energy is the energy released when gaseous metal cation get hydrated. Mgn plus react with 6H2O give MH2O6N plus hydration energy. Hydration energy of a metal cation increase with increase in effective nuclear charge and decrease in ionic radii. Because these two factors bring the water molecule closer to the metal cation, Mn plus resulting in the increased electrostatic attraction between the metal cation and the water molecule. A dipositive transition metal cation of 3D series, the effective nuclear charge increase and ionic radii decrease across a period. We expect the electrostatic attraction between metal cation and the water molecule increase regularly along the transition metal series. Therefore, the hydration energy should increase regularly from cation 2 plus to Zn2 plus, and a straight line should be obtained as shown by dotted line in figure 4.15. In fact, There are some deviation from a linear relationship. When a dipositive or a tripositive metal cation of 3D series transition metal get hydrated, a high-spin octahedral aqua complex is formed. Therefore, not only the hydration energy but CFS is also involved. Thus, experimental hydration energy is the sum of theoretical hydration energy and CFSC. Experimental hydration energy is equal to theoretical or expected hydration energy plus CFSC. Experimental hydration energy is equal to theoretical or expected hydration energy plus CFSC. In calcium, Dn is 0, scandium 1 is there, titanium 2 is there, vanadium is 3, chromium is 4, magnesium is 5. Then in iron 6, cobalt 7, nickel 8, copper 9, zinc 10 at oxidation number 2. Hydration energy in kilojoule per mole. Hydration energy is increasing from calcium to vanadium, and then the energy is decreasing from chromium to manganese. Then hydration energy is increasing from manganese to nickel, then it is getting decreasing from nickel to zinc. If the experimental hydration energy for dipositive metal ion of 3D transitions element are plotted as a function of atomic number, a double humped curve is obtained. Figure 4.15. The two hump is curve are due to addition or contribution of CFSC to the expected hydration energy. Since the CFSC of calcium 2, manganese 2 and zinc 2 ion in high spin octahedral complex is 0, therefore the hydration energy of this ion lie on straight line and does not deviate from the experimental value. For a particular metal cation, it is possible to calculate the net contribution of CFSA to the hydration enthalpy. Second, lattice energy. Lattice energy is a change in energy when 1 mole of an ionic crystal is formed from its constituent gaseous ion. M plus free ion in gaseous state react with X minus free ion gaseous state to give Mx in solid and release lattice energy. From the Born-Land equations, lattice energy U is equal to minus N0 Az plus Z minus upon R0 multiplied by 1 minus 1 upon 9. That is, lattice is directly proportional to Z plus Z minus upon R0, where N Avogadro number, A Madelung constant which depend upon the geometry of the crystal, Z plus and Z minus are the charge on cation and respectively R0 is inter-ionic distance, N is Born exponent. According to Born-Land equations, the lattice energy of an ionic crystal increase with increase in product of Z plus and Z minus and decrease in inter-ionic distance R0. The lattice energy for halide or dipositive metal ion of 3D transition element should increase from calcium 2 plus to zinc 2 plus ions, and a straight line should be observed as shown by dotted line in figure 4.16. In fact, there are some deviation from linear relationship. Some transition metal compound have higher measured lattice energy obtained by calculation using Born-Haber cycle than that of expected calculated by Born-Land equation. In contrast, the experimental and theoretical lattice energy for main groups are in close agreement because this compound do not have CFSC. In the ionic crystals of halide of dipositive or tripositive metal ion of 3D series transition element, the metal cation occupy octahedral void. Therefore, the coordination number of the metal cation is 6. The arrangement of halide around the metal cation is analogous to high spin octahedral complex. Therefore, the CFSC contribute to the experimental lattice energy. Thus, contribution of CFSC causes the higher experimental lattice energy than the expected. Since CFSC value for different metal cation are different, therefore experimental lattice energy increase irregularly from calcium dihalide to zinc dihalide. If the experimental lattice energy for CaCl2 or ZnCl2 are plotted as a function of atomic number, a double humped curve is obtained. Since CFSC for Ca2 plus D0 high spin, magnesium 2 plus D5, zinc 2 plus octahedral field is 0. Thus, ions calcium 2 plus manganese 2 plus zinc 2 plus lie on straight line. For every field octahedral field, vanadium 2 plus D3 and nickel 2 plus D8 have the greater CFSC minus 1.2 delta 0. Therefore, these two ions show two maxima and the curve above the straight line. Lattice energy in kilojoule per mole. Lattice energy is increasing from calcium 0, scandium 1 till titanium 2. Then it is yes until vanadium 3. Then the lattice energy is decreasing from vanadium 3, chromium 4, manganese 5. So manganese 5 lattice energy is very low. Then manganese lattice energy increases from manganese 5, iron 6, cobalt 7, nickel 8. Then nickel from the nickel 8 lattice energy decrease to copper 9 and zinc 10. This all the transition element is under the oxidation number 2. The correct value of lattice energy can be calculated by subtracting the CFSC from experimental lattice energy. Similar plots are obtained from lattice energy of other MX2 and MX3 crystals. Third, ionic radii of divalent metal ions of 3D series transition element. Ionic radii of dipositive and tripositive metal cation of 3D series transition metal in the low spin or high spin octahedral field might be expected to decrease regularly from calcium to zinc 2 because the increasing effective nuclear charge and poor shielding effect of d electron cause the increase of force of attraction between the metal cation and the ligand, and the ligand may approach the metal cation more closely, but some ions show discrepancies from these regular trends of decreasing ionic radii. The ionic radii of calcium 2 manganese 2 zinc 2 ion is in a weak octahedral field decrease smoothly with increasing nuclear charge because these ions are screened by spherically charged distribution. The D1 and D2 and D3 ions have smaller radii, either in weak or a strong field than expected because electron occupy T2G orbitals which lie in the region between the ligands. The nuclei of these ions are less shielded than if they have spherical distribution of electron. However, their ionic radii in octahedral field decrease from D1 to D3 ions as the nuclear charge increase. In weak field octahedral complex of D4 and D5 ion, electrons are either successive to EG orbitals. The first EG electron causes an increase of the relative radius of D4 ion compared to that of D3 ion because EG orbital pointed directly at the ligand. This caused to a repulsion of ligand and increase in the ionic radius of metal ion in octahedral field. In a weak field octahedral complex of D5 ion, the last electron enters into the EG orbital which causes more repulsion of the ligand and further increase in ionic radius of metal ion in octahedral field. The electron density around the metal cation is spherically symmetric, therefore this ion lies on the smooth line. Its ionic radius is smaller than that of D0 system but larger than that of D4 weak field system. The addition of electron beyond the defined in a weak field octahedral complex lead to a repetition of the same sequence, except that the d orbital now becomes doubly filled. The variation of ionic radii of dipositive metal ion of transition element in weak field complex is as a function of atomic number is shown in figure 4.17. Ionic radii in picometer. Ionic radii is decreasing from calcium, scandium, titanium, vanadium. Then from vanadium, ionic radii is increasing from vanadium, chromium, manganese. Then the manganese, once again, ionic radii is decreasing from manganese, iron, cobalt, nickel. Then from nickel, ionic radii is increasing from nickel, copper, and zinc. For both dipositive and tripositive ions of 3D series transition element, the ionic radii in strong octahedral field decrease until the T2G6 configuration is reached. The T2G orbital lie in the region between the ligand, providing little or no screening of the nuclear charge. The increased nuclear charge caused the increasing force of attraction between the metal cation and the ligands. In case of D7, D8, D9, D10 metal ion in strong field, the electrons are successively added to each orbitals. The first electron added to each orbital causes an increase in relative ionic radius of D7 ion compared to that of D6 ion in strong field because each orbital pointing directly at the ligand causes a repulsion of a ligand. In the similar way, ionic radii increase from D7 to D10 metal ion in a strong field. Variation of ionic radii of tripositive metal ion of 3D series transition element is shown in weak and strong field complex as a function of atomic number is shown in figure 4.18. So, in the ionic radii picometer, so for high spin complex from scandium till chromium, the ionic radii is decreasing. Then from chromium, manganese till iron of high spin complex, the ionic radii is increasing. Then once again, ionic radii is uh, decreasing of high spin complex from iron, then cobalt, nickel, copper. Then from copper of high spin complex, ionic radii is increasing from copper, zinc, and gallium. Okay, but in low spin complex there is some different graph. So in low spin complex, the ionic radii is decreasing from scandium till cobalt. So which element is decreasing? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt. Okay, this low spin complex ionic radii is decreasing. Then from cobalt, the low spin complex is increasing from cobalt then till gallium. So, the element in between cobalt and gallium is cobalt, nickel, copper, zinc, gallium. All these transition metals are in oxidation number of 3. Fourth, fourth structure of spinel. Spinel are the mixed metal oxide having formula of AB2O4 or AOB2O3. where A can be group 2 metals or a transition metal in plus 2 oxidation states, and a B can be group 13 metal or a transition metal in plus 3 oxidation state. The oxide anion form cubic close packed CCP or face center cubic FCC lattice with 4 octahedral voids and 8 tetrahedral voids per Ab2O4 unit. One third of metal ion occupy tetrahedral void and the two-thirds occupy the octahedral void. Tetrahedral voids are double of octahedral void and octahedral void are equal to lattice point. Therefore, number of tetrahedral void is equal to 2 multiplied by number of octahedral void. Number of octahedral void is equal to number of lattice point. Therefore, number of tetrahedral void is equal to 2 multiplied by number of octahedral void, and also number of tetrahedral void is equal to 2 multiplied by number of lattice point. Spinel are classified into two categories: A. Normal spinel, B. Inverse spinel. A normal spinel. In a normal spinel, A2 plus ion occupy 1/8 of the tetrahedral void and B3 plus ion occupy half of the octahedral void. Thus, normal spinel can be written A B2O4. A in the 2 oxidation state, B2 is a 3 oxidation state. Example of normal spinels are MgAl2O4, MgCr2O4, nickel Cr2O4, Mn3O4, CO3O4, etc. These are normal spinel. B inverse spinel. In an inverse spinel, half of the B3 plus ion have exchanged place with all the A2 plus ion. In the other words, A2 plus ion occupy 1/4 of octahedral void along with the half of B3 plus ion, whereas the other half of the B3 plus ion occupy 1/8 of tetrahedral void. Inverse spinels can be represented as BABO4. B in 3 oxidation state, A is 2 oxidation state, B is 3 oxidation state. So, example of inverse spinel are CrFe2O4, Fe3O4, NiFe2O4, MgFe2O4, nickel Al2O4, etc. In general, the spinel have Fe3 plus ion are inverse spinel. Predicting the structure of spinel. An important factor in determining whether a spinel is normal or inverse is the CFSE of the cation occupying the tetrahedral and octahedral void. The metal cation in tetrahedral and octahedral voids are surrounded by 4 and 6 oxide ion respectively. Thus, the metal cation occupy the tetrahedral and octahedral voids are considered to form tetrahedral and octahedral complex respectively. The oxide ion behave as a weak ligand. To determine whether a spinel is normal or inverse, we have to compare the CFSE in octahedral and tetrahedral environment for both A2 plus and B3 plus ion. If CFSE for B3 plus ion in octahedral void is greater than that of B3 plus in tetrahedral and A2 in both the tetrahedral and octahedral void, the spinel will be normal. In CFSE for A2 plus ion in octahedral void is greater than A2 plus in tetrahedral and B3 plus in both tetrahedral and octahedral void, then the spinel will be inverse. Example: Mn3O4, Mn2 oxidation, Mn2 plus reoxidation O4. O2 minus behave as a weak ligand. Octahedral Mn2 plus D5T2 G3 Eg2 tetrahedral E2T2 3. In CFSE minus 4.4 multiplied by 3 plus 0.6 multiplied by 2 delta 0 will be equal to 0. In tetrahedral CFSE minus 0.27 multiplied by 2 plus 0.118 multiplied by 3 delta 0 will be 0. Mn3 plus D4T2G3Eg1. So CFSE in octahedral will be minus 0.4 multiplied by 3 plus 0.6 multiplied by 1 delta 0 is equal to minus 0.6 delta 0. In CFSE 0.27 multiplied by 2 plus 0.18 multiplied by 2 delta 0 is minus 0.18 delta 0. From this calculation, it is observed that CFSC for Mn3 plus in octahedral field is highest. Therefore, it will be stabilized in octahedral void. Thus, Mn3 plus will occupy the octahedral void and Mn2 plus ion will occupy the tetrahedral void, and hence Mn3O4 is a normal spinel. 2. CO3O4, CO in 2 oxidation, CO2 in 3 oxidation, O4. CO3 plus is a low spin in CO3 plus is a low spin in the field produced by oxide ion. Octahedral CO3 plus D6 T2G6 EG0 CFSA minus 0.6 multiplied by 4 plus 0.6 multiplied by 0 delta 0 is equal to minus 2.4 delta 0. Tetrahedral E3T23 CFSA minus 0.27 multiplied by 3 plus 0.18 multiplied by 3 plus delta 0 is equal to minus 0.81 plus 0.54. Delta 0 is equal to minus 0.27 delta 0. CO2 plus D7 T2G5 EG2 CFSE will be minus 0.4 multiplied by 5 plus 0.6 multiplied by 2 delta 0 will be minus 0.8 delta 0. E4 T23 low spin complex minus 0.27 multiplied by 4 plus 0.18 multiplied by 3 delta 0 is equal to minus 0.54 delta 0. Since CFSC for CO3 plus is highest in octahedral phase, therefore CO3 plus will be occupied octahedral and cobalt 2 will occupy tetrahedral void. Hence CO3O4 is a normal spinner. Third, Fe3O4, Fe, Fe2O4. Fe will be 2 oxidation, Fe2 will be 3 oxidation. Octahedral Fe3 plus D5 T2G3 EG2 CFSC is equal to minus 0.4 multiplied by 3 plus 0.6 multiplied by 2 delta 0 is equal to 0. In tetrahedral E2 T2 3 CFSC is minus 0.27 multiplied by 2 plus 0.18 multiplied by 3 delta 0 is equal to 0. Fe2 plus D6 T2G4 EG2 CFSC is equal to minus 0.4 multiplied by 4 plus 0.6 multiplied by 2 delta 0 is equal to minus 0.4 delta 0. In tetrahedral E3 T23 CFSE minus 0.27 multiplied by 3 plus 1.18 multiplied by 3 delta 0 is equal to minus 0.27 delta 0. Since CFSE for Fe2 plus in octahedral field is highest, therefore Fe2 plus ion will occupy octahedral void and Fe3 plus ion occupy tetrahedral void and octahedral void. Thus Fe3O4 is an inverse spinner. Fourth, nickel Fe2 plus O4 octahedral, Fe3 plus D5 T2G3 EG2 tetrahedral. So octahedral CFSC will be 0. In tetrahedral E2 T2 3 CFSC will be equal to 0. Nickel 2 plus D8 T2G6 EG2 CFSC will be minus 0.4 multiplied by 6 plus 0.6 multiplied by 2 delta 0 is equal to minus 1.2 delta 0. In tetrahedral E4 T2G4 CFSC minus 0.27 multiplied by 4 plus 0.18 multiplied by 4 in bracket delta 0 is equal to minus 0.36 delta 0. Since CFSC for nickel 2 plus ion is highest in octahedral field, therefore nickel 2 plus ion will occupy octahedral void and Fe3 plus will occupy tetrahedral and octahedral void. Thus NiFe2O4 is inverse spinels. Most of the spinel have Fe3 plus ion are inverse spinel Fe3 plus ion and with D5 configuration as CFSC equal to 0 in both octahedral and tetrahedral void. A dipositive ion in the spinel will have a greater CFSC in octahedral field than that in tetrahedral geometry because the crystal field splitting is tetrahedral geometry is 0.45. that of the equivalent octahedral environment. Thus, a dipositive ion will prefer to occupy the octahedral void. Note, if we calculate CFSE for A2 plus and B3 plus ion in only octahedral field, then it is concluded that if CFSE of B3 plus is higher than that of A2 plus, the spinor will be normal spinor. If CFSE of A2 is higher than that of B3 plus, then the spinor will be inverse spinor. Limitation of crystal field theory. Crystal field theory explains successfully the structure of complex magnetic property, color, and electronic spectra. Thermodynamics kinetic aspects of the complex. However, this theory has some serious limitation. First, CFT consider only the metal d orbital and s and p orbital ignored. Second, this theory has not considered the covalent character in transition metal complex. Third, CFT has also not considered the pi bonding, either the m giving electron to L or L is giving electron to M in complex. 4 CFT cannot explain the relative strength of ligand as given in spectrochemical series. Fifth, the compound like chromium carbon monoxide 6, hexacarbon monoxide 6 and nickel tetracarbon monoxide in which metal is in zero oxidation state and the ligand is neutral have no electrostatic attraction between the metal and ligand. Evidence for metal ligand covalent bonding in complex. In first, chromium hexacarbon monoxide is a volatile compound and nickel tetracarbon monoxide is a liquid. This indicates that there is a covalent bonding between the metal and the ligand instead of the ionic. If there would be ionic bond, then the chromium hexacarbon monoxide should be non-volatile and nickel tetracarbon monoxide should be solid. Second, the electron spin resonance ESR. The ESR of iridium hexachloride 2 suggests that the single unpaired electron is only 70% localized on the metal atom and about 30% is localized on the chloride ion. This indicates that there is a sharing of electron and hence some covalency between metal and ligand. Third, nuclear magnetic resonance NMR. The fluorine NMR has detected a delocalization of electron in the fluoro complex of paramagnetic metal ion. It is possible only when an unpaired electron spends more than negligible time on 19 fluorine nucleus. Fourth, nephloxatic nephloxetic effect. The electronic repulsion in d orbital of transition metal cation give rise to a number of energy levels depending upon the arrangement of the electrons. In d orbital, the energy difference between two energy state can be expressed in terms of interelectronic repulsion parameter called the Rash parameter P and C. The difference in energy between the two levels have same spin multiplicity can be expressed in two terms of only B, and the difference in energy between two energy levels having different spin multiplicity can be expressed in terms of B and C. It is observed experimentally that from electron spectra of complex that the magnitude of B and C decrease when the complex is formed. The reduced value of B and C indicate the electron density is reduced from metal cation. That is, electron cloud is delocalized over both the metal cation and the ligand. This suggests that there is some covalency between metal cation and the ligand. The more the value of B and C is reduced, greater the delocalization of electron cloud and greater the covalency. The delocalization of electron cloud over metal cation and the ligand is called the nephloxetic effect. Fifth, nuclear quadrupole resonance (NQR). The NQR spectrum of some complex containing halide is ligand like platinum tetrachloride. Palladium tetrachloride suggests that metal ligand bond is partially ionic and partially covalent.